I titled it kind of ambitiously, but we'll see what happens. Right? So this talk is based on 2 papers, kind of like a recent line of works that I'm very interested in, which is like transformers. The first one is it will be presented in Europe this year. Transformers learn to implement preconditioned gradient descent for in-context learning. It's a joint work with wonderful collaborators, Xiang Chang and Hadi Danishman. They're all postdocs in our group, and Surabhi Shah is one of my advisors. The other work we just wrapped up, linear attention is all you need, maybe. It's work by Xiang Chang, Ali Javabe, Surabhi Shah, Ali and Surabhi are my advisors. And my colleagues from Korea, I went to KAIST too as an undergrad, Minhak and Charji. All right, so let me start, this presentation with large language models. We're like all excited about large language models. And I didn't prepare any like slides for like, oh, this is impressive, ChatGPT impressive, like this obligatory slides, because I'm sure you guys are already seeing a lot of that. So let me just get to the business. All right, so LLMs have shown like incredible performance in many, many applications. And for those who are not familiar in the audience, it's based on a neural network architecture called transformers. It's developed by Google back in 2017, right? Attention is all you need. I mean, the attention, all these things were like there even before, but transformer term was kind of coined in this paper. So the $1 million or $1 billion or infinite source of money question is, do we understand the working mechanism behind like how these language models work, right? I mean, as impressive as the question is, it's just very hard to answer. And one of my collaborators, Sebastian Bubat, some of you guys might have been to the talk early this year, Sparks of AGI, is from Microsoft Research. He says during his AAAI conference keynote speech, during his speech, he said, the truth is that nobody has a clue about what's going on. Like we don't know nothing about what's going on. We just see a lot of applications, but we really don't know how it works, what's the working mechanisms, how you like really actually train it, and so on. We don't even know how many parameters GPT-4 have, So what's the main difficulty? As you all know, modern neural networks are just crazy, especially transformers. They're too large scale and super complicated, like 100 and 1,000 billion parameters, probably this entire room will be filled up with the parameters if you print out the parameters in the A4 papers, print papers. So then are we just gonna give up, right? I'm coming more from like a theory background. When I see like a challenge, I try to like understand it theoretically, but then I see like 100 billion parameters. I'm like, oh, what should I do? Yeah, it's like very challenging, right? So are we giving up? But the thing is like neural network itself is like kind of, it's like a large system of interacting like parts, components, a lot of components. But then somehow like it shows like emergent behaviors, like, it seems to have like artificial general intelligence, AGI, stuff like that. So something emerged with a huge scale, large scale system with interacting parts. But then, well, like if you look at the field of physics, I'm not an expert in physics, but I took some college level physics classes. But what they did was exactly that, They come up with some principled models for very complicated systems and try to like come up with some rules of dynamics and stuff like that. Try to understand like this like giant large scale system of like interacting things. Well, and if you look at the physics, like there are 2 pillars, basically, and it's my opinion, also Sebastian Bubat's opinion. The control, it's built precisely on controlled experiments. You control like all these variates and see what happens. And toy mathematical models. We have like Newton's law, we have this harmonic oscillator, which applies to everything, right? So we have like this basic principles that we can use to understand like the large scale interacting particles or parts. Also, Ben Recht, he's visiting today, right? He's my hero. Probably he doesn't know me, I watch a lot of his talk, and during his ICML 2018 tutorial on optimization perspective on control, whatever, he said something like this: if machine learning models do crazy things on linearized models, it's going to do the even more crazy things on the complex models. Okay? So the point being, if you can understand its behavior on the linearized simple models, how are we going to understand its behavior on the actual system, right? So I'm going to build on this throughout the talk. And so what is this talk about? So we're going to try to understand. I'm not going to overclaim and say I understand everything. I just maybe scratch the surface of like large language models. But my goal is to understand, like in a principled manner, like what's going on, building on controlled experiments and simple models. Okay, so I'm going to talk about something called in-context learning. I'm going to talk about like what it is. So those who are not familiar with this term, bear with me. So that will be based on the first part of talk will be based on like this paper that I'm going to present in Europe this year. And the second part is more about like intriguing questions wise type of research question, which is like about unconventional features of transform optimization. And this will be like the second part of the presentation. And at any time you have a question, please feel free to interrupt. Yeah, I'll try to answer the questions. All right, so let me start with the first part, which is in-context learning. What is in-context learning? So large language models, as GPT model, ChatGPT, are able to perform something called in-context learning, which is given a prompt containing examples from a task, input-output pairs, and then you provide a new query input that you want to get the answer about. Then the language model, without changing their weights, without fine-tuning their weights, will answer that question. So what I mean by that, just give me an example. Let's say, by the way, is this German or French? I don't speak neither of the language.
It's French.
French, okay. Let's say you want to translate from French to English, right? You give a, it's probably not mason, mason house, and cat, and then you provide like a French word in dog, and then you put that as a prompt to the language model, they will answer, oh, it's dog. I didn't even tell that transformer, it's like a translation task. All I did was providing some examples. It's like basically machine learning. Provide examples and the model learns it and answer the question. And all that can be done in the prompt, just like in the ChatGPT, you just put the examples, like, you know, bunch of pairs that you want to get answers from, give them some examples and put the query that you want to get answer from, and then language model will understand the task and then just automatically answer the questions. For AI engineers, this is like a revolutionary way to fine-tune your model to the downstream test, because you literally don't have to change any weights. You just need to provide the right context that it will just learn from the context. And this phenomenon is, yeah, very like kind of revolutionary when it came out. I think it's kind of started out in a line of work, including like 2020 large language models or few-shot learners, including that famous paper. And then the question I wanted to ask, seeing this, was like, what mechanism do large language models use to achieve this remarkable property? So, so we're gonna first talk about in-context learning and try to understand the mechanism behind it. And as I alluded before, my hero, Benjamin Recht, he has this nice linearization principle. If machine learning models gonna do crazy things on linearized model, then it's gonna do even more crazy things on complex model. So let's linearize everything. If you cannot answer the question for the linearized model, there's no hope we can answer it for more complex, fully fledged GPT or transformers. So in this talk, since we only got like 30 minutes, I'm not gonna go into like any like mathematical equations defining transformers and like attention. I'm just gonna take that as black box. And if you're interested, you can just look up YouTube. Like, you know, there are like thousands of YouTube videos out there trying to explain what transformers are about and what the attention mechanism is about. So basically, attention mechanism is like the building block to build a neural network architecture called transformer, and that transformer is a building block for ChatGPT. Okay. Then our saying is what? we consider just a single hat, just one block of transformer, which is linearized, as in we don't add any nonlinear activation to it. Usually, like the transformer, when you look at the potential is all you need paper, it comes with softmax and nonlinear activation, and but we just disregard that. So we just take that linear attention and just repeat them, stack them L times. That's like the linear transformer that we consider. Simple as possible. And task is also linear. We're gonna ask that to solve linear regression in context. Go ahead.
So do you have nonlinear activations outside of attention? Or in the whole model, there are no softmaxes or nonlinear activations?
Just attention block repeated.
Okay, so no fully connected blocks, just
no.
Got it. Okay.
Yeah. Simple as possible, yeah.
Is it an attention block technically cubic?
It is nonlinear, but I'm saying like I don't add extra nonlinear operations on top of it. Okay. So the training data set will be the random instances of linear regression. Again, I'm not going to write it down in the mathematical form because we don't have time, first of all. Yeah, go ahead. Oh, do you have a yeah, in the back.
Oh, you probably a quick way to think about, you're saying that the attention is inherently nonlinear, you can actually remove the things. Is there a way to think about that? Like how to see
I'll tell you about it offline probably, because it might not be relevant to talk. Yeah, but very good question. Yeah. Go ahead.
Straightforward way to see that when you linearize it is not a special case of a linear MLP.
It's not, because a short answer to that for those who are curious is that MLP is at the end of the day you have output, and how many layers you have. It's like a linear function on the data, right? Y is a linear function on data. How many layers you have? Maybe in terms of the weights is nonlinear, but the attention is X will appear multiple times in between. So it's just genuinely nonlinear. All right, so let me remark that we're not the first one to consider this setting. People are smart. They tend to linearize things when they when they don't understand things. So this inspiring work from actually it's from Google too. They consider this setting, but then they study more empirically. So, but then I'm coming more from my theory background. So what I did was sit down and analyze this training loss landscape. So here are the results. I'm not going to go into the proof. I'm not going to go into the formal statement, but it roughly sounds like this. So under the setting, let's say the L, capital L, the number of layers equal to 1. So it's just like a one block transformer. And luckily, I was able to analyze the global minimizers of the training loss and show that that corresponds to implementing one step of a preconditioned gradient descent. And what's remarkable about this result is that the preconditioner that the transformer learns not only adapts to the data distribution, but also kind of like a data inadequacy due to fine sample. And all this time, I'm not going to go into the details. Come talk to me if you're interested, or look at my paper. And this special case of this theorem, when the inputs are all isotropic, proves the empirical observation in this Von Oswald paper that I mentioned earlier from Google. And I'd like to also kind of remark that shortly after our work, so probably concurrent work from Peter Bartlett group in Berkeley, they showed that actually randomly initialized. So what I did was a landscape analysis, global minimizer of the objective, and they showed that running gradient descent with the random initialization will converge to that minimizer, which is non-trivial because objective is not convex. So you will never know whether it will get stuck at the poor local minima and so on. Go on.
What do you mean by it's trained on random instances of linear regression?
So random instances, okay. Can I take that also to offline? Because it's very easy to answer, but I have to write things down. And is that okay? All right, check. More layers. We weren't able to analyze a global minimizer. As layer gets more complicated, it just becomes incredibly more and more complicated. And what we were able to show that a subset of stationary points where the gradients vanishes corresponds to implementing L steps of preconditioned gradient descent I mentioned earlier. The remark is that when we run experiments, with the random initialization and run like Atom, SGD, whatever, always finds that stationary points that we characterize. So we kind of conjecture that those stationary points are indeed like local or maybe global minimizer. And those are for the audience in the audience who might be interested in like a follow-up. So this is like the end of the part one. Part two, let me get into like more optimization aspect. So I will talk about the in-context learning. I'm going to talk about the transformer optimization, basically like how the GPT is made. All right. So observation over the last 10 years, if you look at the literature closely, they notice that transformer training is just notoriously difficult. It requires a careful design of optimizer as well as various heuristics. There are so many papers out there. Yeah, I cannot even survey all these papers in this room. So it's like just very difficult. And it has like a bizarre phenomenon. And in order to talk about that, I'll first have to review some optimization 101. So whirlwind tour of optimization theory is that I'm gonna like bring up several concepts that optimization people love to use to analyze the algorithms like gradient descent. So assuming f is like sufficiently differentiable, they often use this Lipschitzness, saying like the gradient is like bounded by some constant, or smoothness, Hessian is norm is bounded by some constant, or strong convexity, saying like the loss has to be sufficiently like strongly convex. Condition number is like how like distorted your landscape is. And most importantly, people have been using a lot of the stochastic gradient noise assumption where, so in your mini batch gradient descent, stochastic gradient, its variance is bounded by something so that you can control the variance in your analysis of SGD. So why are this concept important? So just believe me, like people use this concept a lot in the optimization analysis. It's because like all the analysis of gradient descent algorithms as SGD or Atom, whatever, they typically depends on these parameters. Their convergence rate, how fast they converge, depends on these parameters. So for example, if like the condition number is small, you can show that gradient descent converges in fewer steps. Right? But the several recent works have connected these difficulties of transformer to the unconventional features relative to these concepts. So let me talk about that shortly. So the first feature is that for transformer training, Atom is just strictly better than SGD. So let me show you some plots. And so I'm just like going to show you some plots from like all these nice previous works. So as a baseline, we in machine learning 101 class, we love to train convolutional neural network to classify images. For those tests, so red line is Atom, black line is SGD. SGD is just as good as Atom. Okay, plus M, minus M is like with momentum, without momentum. Not so important at this point. But SGD is just as good as Atom. And actually, one of our faculty, Asia Wilson, who's also in LIT or ECS faculty, she like back in 2017 had a paper about this too. She said adaptive methods are marginal. Like the values of adaptive methods are marginal. It's a really great paper, by the way. But then look at the transformer training. There's a strict gap between adaptive methods like Atom and SGD. Adaptive methods are just strictly better. So if you look at this conventional training that you've done in machine learning 101 class, and you try to like use the logic here, it just doesn't quite apply. So it's like kind of curious. Yeah, again, like this like in the literature, it's kind of like convention folklore to say that like SGD is just as good as Atom for the vision tasks. Yeah, but it's like kind of in stark contrast. And yeah, there are two questions. Yeah, you can go first.
Yeah, so I found Atom was SGD with just SGD with momentum.
It's not. It's with I can tell you more about it. Yeah, it's not. Yeah.
You must stay my offline. I'll just ask you offline.
Sounds good. Next. Second feature, I told you that optimization theory people love to analyze with the bounded variance in the stochastic gradient assumption. So this was a plot, but the same setting, when you plot the stochastic gradient noise, you see this. So these first two corresponds to this vision model training. It's like kind of like a very like less heavy tail, right? But when you look at the transformer training, the noise distribution is very heavy tail, as in like it has like a long tail, heavy tail. Yeah, I hope like heavy tail makes sense. It's like a statistical term, right? There was a question, Wanda?
What exactly is buckets?
It's like a full batch gradient, norm of full batch gradient minus stochastic gradient. This is stochastic gradient, and this is full batch gradient. Yeah, and you're just plotting the histogram of it. So clearly it has a different trend, right? Heavy tail versus light tail.
You measure the heavy tail, are you measuring it in terms of say like an L2 norm gradient, or are you measuring it like the direction of the heavy tail in the same
L2 norm.
L2 norm
Yeah.
gradient? I see, so it's like not hyperconvective.
Yep, yep.
You're pooling all the layers into a single vector.
So I couldn't hear this, right?
You're taking all the layers of the transformer and you're pooling them into a single vector, which you know, if you look at the distribution of noise per layer, it's
Oh, maybe they might give you something more, but like, yeah, these plots are just full, yeah.
You expect that the more you pull, the less the tail gets, the more you're
no, because it's different layers have different noise scales, then you just pull them and you think it's some tail, but actually each layer is
Yeah, this is why we need to have more seminars. Yeah, yeah. So that we can crack the problems together. All righty. You had a question, Annie?
No, I can wait.
All right. Feature 3 is an ill-conditioned landscape, and there could be a lot of different ways to define the ill-conditionedness. But Jiang et al., their group from Carnegie Mellon, those who know, like Wenzi Li is on this paper. They define this robust version of condition number, which is like lambda max of the Hessian divided by lambda median of Hessian. And then they notice that, so for training transformer, non-adaptive methods like SUD tend to have larger, so larger condition number means it's more ill-conditioned, meaning it's harder to optimize. So they're trying to understand this issue from the landscape point of view. In other words, they show, they empirically show that R, also they have some theory, R SUD, condition number of SUD is larger than atom. Go ahead.
Sorry, why is the Hessian not a property? Why is it a property of the optimizer rather than of the function?
Oh, because you're measuring along the trajectory. Yeah.
So it's just a 1D curvature.
Like, yeah, as you move along, you measure this at like iterates XTs of the optimizer. Good question. And then so they measure this ratio, and typically you see that like it's twice larger than that of atom. SGD's condition number is twice larger than that of atom, which means that it's going through a more adversarial landscape where it's harder to optimize. And here it's like an average value and like a standard deviation. Okay. And then like feature 4 and 5, I only got 30 minutes. I love to go over this, but yeah, feature 4 and 5, just like flash the name of papers. They're like directional smoothness and gradient flipping perspective by Yang Han and Wenzi Li from Carnegie Mellon again. Their paper title is very, very relevant. It says toward understanding why atom converges faster than SGD for transformers. Yeah. So those who are interested, check it out. And generalized smoothness, this is from our own MIT group. They understand like effectiveness clipping and so on. But for the interest of time, I'll skip the details of this. And then Ben Recht's linearization principle again. So we're gonna, the same setting we use for understanding in context learning, linearized transformer to solve linear regression. We trained that, and surprisingly, we observed the same thing. So this was the plot that I showed earlier. Strict performance gap between atom and SGD, right? And then guess what? When you train the linear transformer, you observe the same phenomenon. Red curve is atom, black curve is SGD. And also these three plots are for three different settings, just so that we don't cherry pick the setting. Yeah, I'm not gonna talk about the setting. It's in our paper. And for various setting, basically whatever setting you come up with, SGD is underperformed, like atom beats SGD in terms of the convergence speed. Okay, so interesting. Like we just have shallow, very humble transformer and humble data distribution, linear regression. Linear regression is what we learn in Statistics 101. And then we see the same phenomenon. Yeah.
Does this SGD have momentum?
Yeah, and this is where we add momentum for both. Yeah. Good question. And heavy tail stochastic gradient noise. We have these not nice, heavy tail stochastic gradient, which makes the optimization harder. And when we plot the stochastic noise for our linear regression setting, we see the similar thing. We see that for many, many different settings, stochastic gradient noise is also heavy tail. For trying to solve this linear regression with the linear transformer, and you see the same phenomenon. Okay, so robust condition number, the ill-conditionedness of the landscape, you see the same thing. It's actually sometimes even worse. You measure the ratio between our SGD over our atom with the momentum actually. Then you see that it's typically like twice larger, 3 times larger, 9 times larger, and so on and so on. And directional smoothness is like the one that I swept under the rug. It's also measuring how ill-conditioned your landscape is. And when you plot that of atom and that of SGD, there's a strict gap between the two algorithms, which is consistent with what Rianzi Li paper observed. So I'm almost done with this. Yeah, I think I made it on time. So what's the benefits of this linear transformer? The thing is, now we're doing training linear transformer, linearized simple transformer without the embedding block, without the fully connected block, without the nonlinear activation, without the softmax activation, and you still see the same phenomena as one that's observed, like the difficulty of training transformers. And the data distribution is not Wikipedia. How are you going to mathematically model Wikipedia? Like, how are you going to model this? But we have like a very concrete distribution, which is random instances of linear regression. It's like very concrete distribution, very concrete architecture. It's very simple, trained on very concrete and simple data distribution. And you see you recover all this phenomena. This is, I think, pretty interesting. And the great thing is like the benefit lies in its simplicity and concreteness, because like now we can like run various controlled experiments. So what I'm not going to talk about, but then what we did in our paper is that we changed the data distribution to make it more heavy tail. Also, I'm not going to talk about like how we made it more heavy tail. For those who are interested, come talk to me, please. And we also like increase the number of layers. All the experiments that we did in the previous plot is for 3 layers. 3 layers, and we increase it to like 4, 5, 6, 7, and so on, and see what happens. And the moral story of our control experiment says the features become more pronounced. All this like gap between SGD and atom becomes more and more pronounced as you increase the number of layers or make the data distribution more adversarial in the sense of like heavy tail. Yeah. So the good thing about like linear, again, this simple setting, linearized setting is that you can run like very controlled experiments and see what happens. And so this is the last slide. So conclusion is that I talked about like, well, we're facing like this interacting parts, complicated system, and you look back at physics, they actually tackle all these like complicated questions with controlled experiments with toy models, good toy models. So that was precisely what I was after over the last like 1.5 or 2 years, and then with the good toy model, we were able to do some concrete mathematical analysis that we saw in the in-context learning, where we analyzed the landscape. And I hope that all this kind of work, not just our works, will like serve as like a stepping stone for us to understand like the main question, like billion-dollar question that I asked earlier, the mechanism of how large language models are learned and operate. So this is what I got today, and yeah, if you have any questions, I'll take some. Thank you. Yes, please.
For the optimization results that we discussed, you have any insight like what specifically volume sources that like so much as the GD, and like what is like more because it's just that assumption is right.
Very good question, and those are the main focus of the papers previous work that I described. They have different theory. Some of them say heavy tail noise, some of them say ill-conditioned landscape, and so on and so on. There are like 4 or 5 of them. And honestly, that's what we need to figure out. Yeah, that's like my direct answer. I'm not gonna pretend that I know the answer. But what's good thing is like we have a toy model that can be run on my Mac within like 10 minutes to see what's the answer. Like, you know, if you have the answer, you can test it on my toy model, see what happens. And I'm pretty confident that it will reflect the full transformer, which takes like a month to train with the exaggeration.
This is where the comment that I think that when you define heavy tail noise, you're putting a metric on the space, but you're putting the metric on the flat parameter space.
Yeah.
I think if you take a different metric,
yeah,
you would probably get a different.
Yeah, very nice comment. Yeah. But I guess we just follow like whatever people did in the previous work. It's like they said, oh, that's the main reason, and they have some theoretical analysis for that.
Right.
Yeah.
They pick the metric too.
Yeah, they picked the metric, and I just followed it. It's like this was more about like, all right, this model is actually legitimate. So in order to do that, I gotta follow like the previous setup. But I do agree that there might be a better way to define the distribution, head to tailness, and try to like reason about it. Let's go first. Yeah, you go first.
So the cool kids have thought that lion was enough, and then you could just like take the sign of the gradient instead of keeping the third parameter.
Right.
Have you tried that?
I mean, so all these papers, they're published in iClear. Like if you just run like Adam, that's like they'll like reviewers like, what about Leon? Like and so like that. So they run it. Adams and Leon are pretty similar, like in the like ballpark. Leon might be a little bit better, but like you know, it's like in the same. So plot will be like something like this. Like all these papers, like they did like Adam, Leon, like all this Ada factor, whatever. And plot will be like this. SGD will be like this, convergence speed. And Adam, Leon, Ada factor. Yeah. So yeah. So I think it's like a matter of we kind of zoom out a little bit and see like what's the major gap. Yeah, I think that's more important question for us. Yeah. Go ahead.
So one thing to that, did you look at the? So one thing that also has been observed is that the activations of these models are also somewhat heavy tail. Do you know so from the optimization perspective, would those two things be linked with like the heavy tailness in the loss? So there's heavy tailness in the loss landscape, heavy tailness in the data.
Yeah.
Would that seems like it would factor into heavy tailness in the activations? And have you?
So what do you mean by the like? I kind of get what you're saying, but like, what do you mean by heavy tailness of the activation?
Okay, so I mean, if you track like say the kurtosis,
Okay.
That's what like in that literature that's what kind of uses like heavy tailness. For example, in your attention model, right?
Yeah.
You have your output of like the first linear layer, then your two queries gives you values, you feed that into your attention, then a dense model. Take any of those outputs of any weight features, so output of the attention module, and graph all of your kind of per channel activations, similarly to what you did here, but isolating by layer. And you will find like it has like a rough Gaussian in the middle and then some heavy tail at the end.
I see what you're saying. So I mean, yeah, I'm not sure like there's a connection between that, and like that would be interesting to see whether like that kind of happens in the linear.
Okay, so you just look at loss lines. You didn't look at like weight activation.
Right. Yeah, it's like truly about the training loss landscape.
Got it. Okay.
Yeah, great questions up there. That'll be interesting. Any more questions? Oh, a lot of questions. Thank you. Yeah, could you go first?
Sure. Yeah, so you mentioned like you love Ben Rex stuff, and I really like his like random features stuff.
Right. Yeah.
So I'm curious if other people have looked at something of that flavor, but for transformers. I don't know what that would be, but like you randomly, do linear combinations of random transformers. Is that any good? Do you know of any?
Do anyone in the audience know the answer to the question? He was asking random feature work by Ben Rex, that famous work. Has anyone looked at like this kind of like random feature for transformer, like kernels, whatever? Yeah, very interesting. I don't know. Honestly, I don't know. Yeah, if I know, I'll let you know. Yeah.
Actually, I just wanted to ask you a question. About what you mean by random realization.
Oh yeah, I can tell you more about. Yeah. I mean, I actually have a backup slide, so it's like this. Like the data is like by random regression, you have a response vector sample uniformly at random from Gaussian. each response vector corresponds to one linear regression problem, right? W0 star, which is drawn, and you have like a bunch of xi's, that's like one linear regression instance. And you sample w's and xi's randomly. Yeah, that's what I mean by random linear regression instances. Yeah. Any more questions? All right.
Do you know, like, how expressive do you think these models are? Like the linear.
So expressivity, like, you know, even like ReLU network, if designed properly, it's a universal approximator. Transformer is the universal approximator. But then everything is universal approximator. But then why ReLU network doesn't create ChatGPT and transformer create ChatGPT? I guess like that's the question we need to answer moving forward.
Is just like attention universal approximator?
There's a paper about it. Like I cannot like write down the theorem right now, but yeah, transformer is like a universal approximator for a sequence-to-sequence model. Yeah, it's like a paper about it. Actually, one of my colleagues, Charlie, yeah, he was actually an MIT PhD too. Yeah. Yeah, I guess like we're kind of over time. We need to go to Ben Rec talk. So yeah, I'll wrap it up right here. And thank you so much for joining us.